was fun.
We got it. We got it. Well, you guys, for me, this is not an easy task. I mean, logic is a huge field. And so today what I thought I'd do, since you asked me to start at the beginning, just going to layer this with multiple layers in terms of the more simplistic way of looking at symbolic logic. Get more sophisticated until I get to the point where some of you really wanted me to give a presentation on calculus aspects of using logic, particularly with the epsilon delta person with limits. So, let me start from the beginning. I think there's some very basic operations we have in propositions. A proposition is nothing more than a funky word describing a statement in English that can be true or false. For example, this room has a light in it. That's a proposition. But there's ways of combining propositions to make more complex propositions, and we have rules of logic that allows us to observe the validity or identify the validity of these individual arguments. How many of you in here have taken a logic course? Catherine?
Logic was included in my geometry course in high school.
In high school? Critical thinking count?
Yeah. High school logic and debate course kind of mixed together, I guess.
Okay. Yeah.
It came more from the liberal arts side than the math and science side, but
Gotcha.
the same basic axioms.
Well, you know, for me as a mathematician, my background is in abstract algebra, the foundations. So for me, it may be true that a lot of scientists say that mathematics is a foundation of sciences, but logic is really the foundation of mathematics. Oh, you guys, I forgot something. Do you mind? During the last class, my wife called. The car's having problems, so in case you get stuck, can I do this song?
Can I record you?
That's fine. So, everybody, let me talk about some simple ways of combining statements, or propositions. Here's one way to do it. Now, I'm using funky little symbols, but that upward V is what I refer to as my disjunctive connector. It represents the word or in English. For us math people, we can also, in set theory, think of that as a union symbol. The union symbol corresponds to that disjunctive connector, the word or. Here's another one. If I use an upside-down V, I refer to it as my conjunctive connector. It simply represents the word and in English. It's a way to take two propositions and combine it to a more complex proposition. Again, for us math people, we often use an intersection operation for sets. It means the same thing. And here's another very important connector for propositions. I use a single arrow key, and it simply stands for the phrase, if P, then Q. I sometimes classify that as a conditional statement. But in logic, we spent some time, we want to devote some thought to identifying when these particular statements are true. And I think for the very first statement, it might be true, it might be false, but it depends on the true or falseness of the individual propositions. So, I built what I refer to as a truth table to identify the validity of such a proposition. Let me show you an example of the truth table. I think the statement P and Q themselves individually might be true. Bless you. Or false, and I think those are the only four possible combinations I can have for these two propositions. Yeah, Matthew.
That looks very similar to like Boolean.
Yeah.
Boolean algebra.
See, to me, a Boolean algebra is nothing more than everything I'm saying in disguise, because a Boolean algebra is simply an algebra consisting of on and off gates.
Mm-hmm.
Yeses or nos, zeros and ones, or true and false. It's all the same thing. I think those systems are in a sense, equivalent. But we'll talk about that if we get Math 15 running. How many of you signed up for the Math 15?
We can't sign up because...
Well, I meant sign the paper, I meant.
Oh, yeah.
Oh, yeah.
And everybody, we have a convention. We kind of want to interpret the statement P or Q to be true when either one of these P or Qs individually is true. So my truth assignment for this disjunctive connection is true whenever either P or Q is true, and false otherwise. You can literally treat this as our definition of what it means to say P or Q as a whole new proposition. I think also with a truth table, I can use this for my classification of conjunction.
This is how you like set up a circuit board, right? If you're designing one.
Very much is what you do with a circuit board, absolutely. And again, with the circuit boards, I'll go through that in Math 15.
Okay,
Same thing.
in review of the pre-calc class I had with you in the summer, which is cool. Okay, so the and the or, which is the intersection and which is the union?
The intersection always corresponds to the word and. So
Okay.
that would correspond to this operation between propositions. It's just the intersection is a connection between sets as opposed to
Okay.
propositions. I maintain that we have a convention of attributing a truth value to this compound statement when both P and Q are true. And a false assignment when either P or Q is false. Again, here you guys can almost treat this as a definition of what it means to have a statement P and Q. I think for a conditional statement, this one's a bit more tricky. For a conditional statement, we tend to think of a conditional statement as being false. When P is false, I misspoke, when P is true but Q is false. And so for my truth assignment for P implies Q as a statement, is I will merely assign a false value in this particular case and a truth value everywhere else. Now the other thing tricky about this is when it comes to P being false and Q being true, why is it the case that we consider P implies Q to be a true statement? Something, Catherine, you and I discussed last time. You didn't like my argument. It's as if nothing is really going on with the assumption P. It's as if P is going to be false. Anything goes for the truth value for Q. And so it doesn't even matter whether Q is going to be true or false. The conditional statement you attribute a truth value to. I can say it another way. I can show equivalency between this and a different way of representing conditional statement. So, what about this one? Not one of my standards, but if I negate P and disjunct with Q, let's see what I get.
The one symbol that you use for negate? Oh, okay.
Actually, that's a good question. I don't know. Every book you open is slightly different. A lot of texts use my cedille. Some use a negative sign. Some use this awkward L shape. I see so many different ways to
I've seen
represent
an
negation.
exclamation point in front of the,
Have you really?
yeah, in computer science.
Yeah.
You mean like this?
Yeah.
Yeah, that's
That's
not.
interesting. I've never come across that.
Yeah.
You could always
That's not-
confuse
No.
it with
Yeah. In
factorial.
computer science,
I was going to say the same thing. Yeah.
if you're writing a if-else statement and you're saying like, if something or other is not equal to something or other, you would put an exclamation point in front of the equal sign, generally. In Java
I
in
just didn't know
particular, yeah.
See, I don't know the visual-based languages.
Yeah.
So you guys, check this out. Let me build a truth table describing the truth value for a not P or Q. Well, here's not P. It's simply the truth values already have a P. They're just going to be negated. And if I connect P with Q, I misspoke, didn't I? I meant to connect negation of P with Q with my disjunctive connector. Let's see what I get. In the very first row of my truth table, I think not P is false, Q is true, and so this value is going to hold to be true. I think when it comes to not P being false, but Q being false, the truth value over here is going to be false. Now let's see what Q is going to be in the third row. Q, I can't read it. Q is going to be
Q is true.
so this will be irrelevant. We wouldn't have to go that far because I think the negation of P is true in both cases. So I think for free, no matter what happens with Q, I got truth values. So if you don't like the idea that the assignment of my F's and P's in this particular row right here is going to be true, look at it slightly differently. Just look at this alternative version of P implies Q. I think this is the same as P implies Q because they have the same truth values.
So you don't even have to look over there because you just look at that.
Exactly. And if I've already got truth values for these propositions, and it's a disjunctive connector, who cares about the other one? It's automatically going to be true.
So for the P implies Q, why is it in that specific pattern? Could you explain that? I'm a little lost.
You can literally treat that, as well as this column, as well as this column, as a definition of what these particular compound statements really mean. It's sort of like I'm saying, from now on, if you see a conditional statement P implies Q, we will define it as meaning it's got these truth values. for these corresponding truth values for P and Q.
Okay. But, okay, I guess, I don't know, that doesn't sound like a good enough explanation for P implies Q for me. Because yes, I can memorize that pattern, but then the next day I could also forget it. So is there a better way to remember it?
There's a better way of remembering it, but keep in mind, I can literally treat this as a man-made definition, as opposed to something I can prove. I will from now on define the validity of a conditional statement in this fashion, that my P implies Q statement is going to be false only when the premise is true and the conclusion is false.
Okay.
So let me give you an example of a conditional statement. If it's raining, then there's got to be some clouds up there. That's a conditional statement. I just think its truth values are equivalent to this. It's either not raining or there are clouds up there.
What?
I think they're equivalent statements. After all, you check out these two columns. They got exactly the truth values.
Either it's not raining. You know, that does make sense, okay.
It's an equivalent statement.
Could it be half true, half false?
Ooh, yes. That's a really good point. Where do you do that? You're talking about a whole nother field of mathematics. It's called this. I'm not making this up, by the way.
Fuzzy?
Fuzzy.
Yeah, or maybe I don't have these notes.
Who coined that phrase?
Because of what she said, well, maybe the truth value down here is somewhere between false and true. Maybe not even halfway, maybe at various different positions.
Like a half truth?
We can deal with fuzzy logic.
So like, okay, relate this to computers, like normal computers, they calculate between 1 and 0s, and then like
Yes.
quantum computers go between 1 and 0. So would that be fuzzy logic, the thing between 1 and 0?
Yes. Because you're treating your ones and zeros as your truth and false assignments.
But can't quantum computers say true and false?
Yeah.
Oh yeah, they say.
Yes.
Yeah.
That's true.
So you're saying that,
Sorry, I stalled because I'm thinking of something. I'll say it in a minute.
So in the P arrow Q, P
Yes.
then Q, it's if P is true, then Q is true, and if P is false, then Q is false?
Quite the contrary. I'm saying the statement P implies Q. The whole statement. We're going to assign a truth value to it if the premise is true and the conclusion is true, or if the premise is false and who cares about what the conclusion is. We'll consider that a true statement.
So if the premise is true, then no matter what, the conclusion is true?
Quite the contrary. I
I
think
mean, if it's false, no matter what, the
I
conclusion
think this assignment from P and Q says that P is true and Q is true. And if that's the case, then we will assign a truth value of true for the conditional statement. It's only when the premise is true and the conclusion is false will we consider this particular compound statement to be false. And it's a way for you and I to analyze arguments.
Can you give me an example of the third row? In P and Q?
Where?
Third row.
Now, I intentionally wrote it this way because I don't want you guys to look at the sentence and say, oh, it's true. It doesn't matter if it's nonsensical because you and I are just talking about the logical structure of the argument. Well, it's not an argument yet, I'll get there. It's just a proposition. However, if it is the case that,
Why wouldn't you
cat's not
feed your
hungry.
cat?
What's that?
Why wouldn't you just feed your cat? That's so mean. Like what?
This sounds
Walk away from it if you got hungry.
It's a big cat.
It's so Maddie, I'm just suggesting that I would consider this compound statement, this conditional statement, to be having a truth value of true if it were the case that my cat's not hungry. And who cares if I take a walk? And that's exactly what the third and fourth rows down here would say. If you're,
It's not necessarily true, that's just like there's no proposition.
well, I think that's a proposition, it's a statement. It's a statement because it's either true or false.
So if the cat is not hungry, you won't do anything.
No, I'm just saying if the cat's not hungry, if P is false, who cares what Q is because my conditional statement is gonna be true. We assign T truth value to the statement.
So you will always.
Because it's almost as if this is a requirement for me to take a walk, and if I don't meet that requirement, who cares if I take a walk?
I just don't, the terminology is weird.
Yeah, maybe the terminology is, maybe some of the symbols are, but you have to confess, this comes back down to basic English. I'm just providing a logical structure to the English.
So, the last part will always be true, you'll always take a walk if the cat is hungry or not. Is that what it's saying?
That's not really what I'm saying. I'm saying that if my cat is hungry, and if it is the case that I am taking a walk, then I will assign a truth value of T for this particular conditional statement.
Okay.
That's all I'm suggesting. So can you guys appreciate that when you take a peek at this column and this column, they've got equivalent truth values. Sometimes they say in English the statements are equivalent. The statements as propositions are equivalent. I got a nice way of writing it sometimes. Sometimes I just simply say, well, this proposition and this proposition imply each other. And I use a double arrow to suggest that. And the validity or the truth valueness for this more compound statement is going to be true if both these B's inside the parentheses have the same truth value. And check this out. Here they got the same truth value. Here as well, here as well, here as well. And so sometimes I can just simply say those statements are equivalent because of some biconditional statement holds true. That's the word I use for that operation, biconditional. So you guys, can we do another one? Let's talk about this argument. So I got 4 propositions. Let's discuss the truth value of this compound statement. To do it, I'm going to build a truth table. To build my truth table, I need P's, Q's, R's, and S's. So watch me in my organized fashion. I think S could be true or false. And that'll hold true for these values for R. Actually, you know what? I need to state that over again. Maybe R can be false, and I'll have to alternate again to get all possible combination of truth values. Oh, but if I do this, Q might be true throughout. Oh shoot, that means it could have been false throughout. Oh, that means I gotta repeat all of these. Oh shoot, here I'll do it.
Yeah, you have.
It's kind of like gray code.
Yeah, very much. And shoot, you guys, I blew it. I missed the P, so I guess P in each one of these cases could be.
So wouldn't it be 2 to the 4th combinations?
Very
Because
nice.
You have 2 options, true and false.
And that's why I'm not going to finish. I think it's too much writing. Because I think now P could be true in each one of these cases. I'll duplicate all of these over again when T is false. And I think in the end I'm going to have 2 to the 4th power number of rows. So I think the number of rows increases dramatically as the number of propositions in the original compound statement increases. So I tend to give up and use a higher level of tools, which I'll get to next.
What are you using the arrow for again?
P implies Q stands for this in English.
Is P then Q?
Exactly. Like in the sentence, if it's raining, then there must be clouds.
So if P is true,
Yes, I agree.
just say it's
Just stay with P. Well, actually, I think it's better to stay with P is false. If P is false, I think the conditional statement is automatically true.
So Boolean algebra, what would that condition be then? Is it be or?
I give up in Boolean algebra. And I just simply use this as an alternative form for it. Because I just prove their equivalency. That way, with Boolean algebra, I don't have to introduce another symbol. I can just stick with the ands and the ors. So for me to come up with more, perhaps, sophisticated ways of looking at the validity of statements, I can do this. Let's see, where am I at? Oh, you already got it on.
Sure.
Or at least say if P is false, you know what I'd say. If false, then we're not gonna do anything, right?
No, I really meant this. If you take a peek at what's inside this blue circle, I will consider this compound statement to have a value T is true. If the premise is false. And the Q is, I don't know, true or false, doesn't make any difference.
So that's actually not, that would be like, if this is not true, then do this.
See, I think you're getting stuck on the connection between the P and Q as opposed to the validity of the entire compound statement. I'm just saying the compound statement I assign a truth value true to when it comes to the premise being false. So don't sit there and say, oh shoot, I gotta deal with Q. Is Q being true or false depending on P? I'm not talking about their interaction, the relationship. That's why I gave you that funky looking example up there about my cat and my walking. They don't have to be related. I'm just talking about the validity of the overall conditional statement.
So, okay, is Q irrelevant? Like, you don't care what Q is necessarily, what you're trying to say?
Q is irrelevant if you know P is false, and Q is irrelevant if you're identifying the truth value of P implies Q.
That's smart.
And that's what you don't like.
It's not necessarily relevant, because if P is true, you have to know what Q is to know if it's true or false.
Unless
No,
it's
that's-
false.
No, that's true, but he asked, I was saying, if you know P is false, then who cares what's going on with Q? I will consider that conditional statement to be a true statement. It seems,
So would you say if the student is working hard, then the grades are good?
yes.
Okay, great.
Matt?
It seems like if the first part isn't true, then it should default to false. That just seems intuitive, more intuitive. But
I'm just tired, can you see that again?
it seems more intuitive that if P isn't true, then the whole thing just doesn't apply and it should be considered false.
See, I disagree.
I know that's wrong, but hey, it seems more intuitive.
What if I told you this? So Maddie, if you show up here tomorrow, I'm going to give you a loan of $100. And you don't show up tomorrow. If you don't show up tomorrow, it's like I have no responsibility of giving you $100 or reneging on that agreement because the premise was not met. And I think if I promised you $100 if you show up tomorrow and you don't show up, nobody's going to look at me saying he's a lousy person because I didn't have to fulfill my obligation because you weren't here. So I don't think anybody's going to have a bad feeling that's a false value towards me by not giving you the cash. Because you didn't meet the requirement of showing up tomorrow.
So it's not like you didn't give it to me. It's
Correct.
Just, it's just you didn't have the opportunity.
By the way, I'm not going to come here tomorrow, okay?
Come on.
Actually, we are here every Saturday, aren't we, except for tomorrow? We did cancel tomorrow, didn't we?
It was fun.
I'm down to come in tomorrow, so
Oh, I thought we canceled it.
we did, but
Okay.
yeah, I mean, I'm
Well,
willing to.
You guys
When I
can
teach
run
Math
that.
33, I usually have a review session every Saturday. We just happened to have an exam yesterday, so.
And if you're not in that class, you can't come, right?
No, quite the contrary, you can come. It's just that we're talking DD stuff, Math. Do you know what Math 33 is? Ooh.
Is that like calc 3 or 4?
After and at the university or college, after 3 semesters of calculus, there are a couple courses that you take. One's called linear algebra, it's very abstract. One's called differential equations, very applied. And most universities across the country do not connect them. Sierra College, well before I got here, decided we don't want to teach those courses separately, we want to combine them into a single course so that we can use the rich language of linear algebra to discuss differential equations. And for students out of the university and college that don't do this the way we do, they never see the connection because one's not a prerequisite for the other. And so there aren't many institutions that really do this, put those 2 courses into one course. So Math 33 is a 6-unit math course. I do know UC Berkeley does this. I know Sonoma State and Chico State, and those are the only other college universities in Northern California who teach it the way we do. And it's a really nice way to study differential equations. Linear algebra, I'm sorry, I don't mean to sound like a commercial, but if you're ever going to take those courses, it would be really nice to take them here because you get to take them together. It's really nice.
Is that the highest you can take here? Or isn't that the last math?
Math 15.
I don't know. See, years ago, I got tired of my Math 33 students complaining. They would say, oh shoot, I took Math 33, now I'm done and there's nothing else to take and I got to be here for another year or semester.
So I resurrected what was on the books that wasn't being taught, Math 15, discrete mathematics. So I increased the unit load, and I basically kind of sneak in other stuff in there, just to make it more interesting for those students who want to take more math.
I just find it funny how discrete mathematics, which is a high-level course, is called Math 15. Well, Math 33, which is...
When I first started teaching it, the
Yeah.
prerequisite was Math D. So in the class, I had all my complaining Math 33 graduates and the Math D students. It was very interesting. I immediately went to curriculum committee and changed the prerequisite to Math 33.
Discrete structures has a prerequisite of Math D.
What's that?
Discrete structures has a
Does it
prerequisite of Math
really?
D.
I never
I'm pretty
thought of
sure, yeah.
Computer science offers a course analogous to it.
I'm not
Structures.
Yep.
just got started.
Zach,
I was gonna ask what the science of Math 15 is. Do we have a green light on it, or?
I passed through curriculum, the college-wide curriculum committee. I don't know, Randall, I don't remember when I did that. A week or two ago?
I think we're trying to decide on a time, right?
Well, how are we gonna get that course, are you thinking of getting that course running next semester?
Yes.
Hopefully.
But how? I mean, how do you do that?
Tell us.
Jeepers. All right, ask me again Monday. Ask me again Monday.
I have a question about like this club basically. Could we invent some things, like a radio or something, or,
What?
Something physical?
yeah, something that's, well, it's obviously that has to do a lot of math, with a lot of math. So could we do that? Because I was.
That's certainly an option, yes.
Okay.
If anybody can come up with a really good idea.
Just like a project for fun.
Yeah, exactly. And we could just present it and everyone could do maybe like group or maybe individual.
If you can think of something like that, yes, and definitely go through
Are you
random.
an engineer?
No.
So let's make a parabolic reflector of some sort.
Ooh, a parabolic reflector.
Yeah.
Yeah, get in the engineering club.
Yeah.
We're building a
Yeah,
boat.
so when's the Saturday study session for the front club?
We meet at 10 o'clock. I usually go 2 hours. Usually by 2 hours, I got my wife wanting to go to lunch or something.
Okay, back to,
So, you guys, I'm tired of all the writing. Can I just stop? We can do something different. Because I think I've got a whole variety of relations. Oh, you're fine. I'm just going to use this. These are basically rules of argument, rules of logic. I even sometimes refer to them as rules of inference.
Objective is math.
Oh, isn't it? Oh, my apologies. You'll see it in a minute. I need to get the focus anyways.
Do you have any recommendations about a good symbolic logic book?
Take John Terry's class next semester.
Best one I've ever run across. Copy? C-O-P-I. I have no idea if it's still in production, but he's excellent. You guys, I'm old. Can you read? Is it focused?
Yeah.
Okay. So,
Yeah.
I've got a variety of rules of inference. One's called modus ponens, which is this. If I've got the statement P implies Q, and I know it's true, and I know P is true, then if you go back to my truth table, Q's got to be true. I refer to that kind of argument as modus ponens. Notice the author of this text is using different notation than I am. I used an arrow, he's using another
Yeah,
sign.
I was thinking that was proper sum, but it was proper sum with the
Do you mean proper
dyslexia.
subset?
Yeah, proper subset is what I meant.
Yeah, it's not what he meant. No.
And
I think-
proper subset with dyslexia.
That's true, that's true. And I think if P implies Q is known to be true, and Q is known to be false, then necessarily P is going to be false as well. That argument is referred to as modus tollens. By the way, these titles aren't really pertinent to this particular author. They're common titles for these
So-
rules of inference.
Is therefore, right? Is therefore really...
My apologies. The triple dots, for those of you who take my classes,
Yeah.
that you understand that everything's a phrase therefore.
We normally would draw a line, or a diagonal
No.
line with that.
I only
right?
draw a diagonal line on the left-hand side if it's the final therefore.
The
Because
final
it proves I might have a
therefore.
lot of
Oh, okay, okay,
therefores. So when you see the symbol in my class, I've always got the last line.
All right.
Hypothetical syllogism. If P implies Q is true, and you know Q implies R, then necessarily P implies Q. Excuse me, I misspoke. Then necessarily P implies R. Does that sound familiar?
Yeah, that looks like deductive reasoning, or is that
Ooh,
right?
yes. Whatever deductive reasoning is. I was thinking you were going to say transitivity.
Oh, yeah, that too.
Now, disjunctive syllogism says that if I know that the statement P or Q is true, but I know one of them, like Q, is going to be false, then necessarily the other has to be true, because this conditional statement is true when at least one of these statements is true.
Wait,
Yes, I'll wait.
so P or Q means that for every single situation, one of them has to be true?
Well, yes, if you looked at my truth table that I raised, for the very first disjunctive connector, it had values of true, 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 false. And it only had a false truth value when both P and Q were false.
Oh, okay, yeah.
And Amanda, you could literally treat that as your definition of what the word or means.
And so if it didn't, if not P didn't imply Q, then the whole statement wouldn't be true anyway, right?
Say it again, I'm sorry.
So if not P, never mind, I get it, okay.
Now, I think a couple other really important ones are simplification. If I know this compound statement P and Q is a true statement, by the way, he's got a dot for and. If this is a true statement, then I know that P is going to be true as well. Because with my truth table, I define P and Q as being true when both of them are true. So if I know the compound statement here, P and Q is true, then clearly each of the components has to be true as well.
So what about division? You divide Q by Q.
Now, unfortunately, this is really standing for the word and. So don't treat it the traditional way you and I do in mathematics. I also think that if I know P is true, I know Q is true individually, then going back to my truth tables, clearly P and Q is going to be a it's going to hold a truth value as well.
I understand these processes, but at the same time, it's the names that are getting me. Like the disjunctive syllogism and all that. What's it called?
See, I like the choice of words. I like the adjective disjunctive because that's my disjunctive connector.
Okay.
Now, I also think addition's got to hold true, where I've got a statement P is true, therefore P or anything else is going to be true as well, according to my truth values.
That's a destructive dilemma.
A destructive dilemma. If you've got two conditional statements joined with a conjunct connector, and you know both these consequences, Q and S, are false. I misspoke. If you know one or the other of the consequences is false, then one or the other premises has to be false as well. That's what it's really saying. Now, how can I prove that? Well, I just have to go back to my truth table. And shoot, darn it, that would imply 2, 4, 8, 16 rows. And I can verify the conclusion. I just think using these instead, I can actually be more fluid with my verifying whether or not a statement is true or false. So can I give you an example of using these? And you guys, I know I haven't gotten to the calculus yet. I'll get there. I'm just taking steps along the way. And jeepers, where am I at? Oh, I need to change this. This is why we call it a smart computer. You know what? We keep going up. Let's keep going up. You guys, I need this to come on because I made up an example last night, but I typed it.
So they don't have to criticize their handwriting?
You gotta remember, I'm still getting your quizzes.
You agree, aren't you?
I'm wondering what's going on with this. So hold that thought, you guys. I'm gonna get it out real quick.
Are you gonna do 30 frames and add 30 frames?
I can't without keys.
Yeah, that's when they're the same.
Yeah.
You see it.
Hopefully when Balagana gets back, we will move through some of the rest of the foundations of logic here. But what all this is really leading up into is a structure that we can use for proofs in math. And this is where it begins. Truth tables are one of the main ways that you can prove or disprove something. I'm hoping we'll have time to get into some of the other methods, proof by contradiction, induction, contrapositives. These are our tools for proving mathematical statements. How many people have seen these truth tables before?
He didn't give one of them back, right?
Okay, so this is kind of review for most of us, but I think that Balagai definitely does have some very interesting things to show here.
That's why I was so sad.
And looking forward to seeing it typed up.
Where are you majoring?
Did you say discrete structures was a prerequisite for discrete math?
No, they're good classes to take. You take both of them. They're good companion pieces to one another.
I was gonna say because I really wanted to take it next semester.
Yeah, just discrete math. If you're going into computer science, it's a good idea to take both because that's just. I mean, it's the foundation of computer science. Yeah.
Major, but it's not.
Yeah. Discrete structures will teach you circuits and stuff like that. It'll teach you some basic programming with Python. And then if you get into the math, he'll add like calculus and stuff like that to it. So it goes a little bit further. You said you worked with that Taylor series in discrete math, right? Did you say something or power series in discrete math or?
Oh, yes. Yeah, I do.
Yeah, and so I mean, there's no way in discrete structures they don't get into stuff like that. I mean, so it goes a bit.
Yeah, remember,
further.
I'm more
Yeah.
mathy when it comes to math 15 as opposed to computer science.
Yeah.
We don't have any dog fans here, do we?
Oh no, dogs suck.
So, you guys, I'm sorry, it was late at night last night. I tried to think of an example to create. I want you guys to just relax and watch me use those rules of inference to come to the conclusion with all the stuff that has ruled the earth. So,
You mean they don't already?
we don't know. So, Archimedes, my cat, eats lunch, or he reads this morning news, and I'm going to stop reading. I need letters to represent these statements.
Yeah.
So here's my first statement.
L for one.
Either Archimedes, my cat, eats lunch. I'll label that proposition with an A,
Okay.
so I can remember Archimedes eats lunch. Or he reads the morning news. How about N for news? Oh, I forgot the key word, the most important word. If either Archimedes eats lunch or reads the morning news, then